Hello all and welcome to the video for Algebra Lesson 6. This lesson has to do with Chapter 1, Section 7, which starts on page 49 in the book. And this section has to do with functions, okay? So this has a very relevant to what we did in the last section, which had to do with relations. So knowing everything that we know about relations, we're going to use that here when we talk about functions, okay? So right off the bat, what we want to do is we want to define what a function is, okay? So we'll start here. Function, definition of a function is a relation in which each element of the domain is paired with exactly one element of the range, okay? So big emphasis on this exactly one, okay? And you'll see why when we look at some of the real world examples, why functions are important and why we need this to happen. So what we've got here is each element of the domain. Well, what's the elements of the domain? Well, those are the x values, okay? So another way to say this is a function is where each x value is paired with exactly one y value, okay? And that's exactly what we see with these mappings here, okay? Now, not just with the mappings. It's easier to see a function with the mappings, but this also works with tables, graphs, as we'll see later on. So tables, graphs, mappings. You can even just look at the ordered pairs and see if an x value is paired with exactly one y value, okay? So here are two examples of functions by mappings, okay? So if we look at these are mappings. Well, what do mappings look like when they're functions? Well, a basic one here is if you have in the domain -3, 0, 2, and 4, and then everything gets mapped straight across to 5, 3, 2, and -1. So that means -3 is mapped to 5. 0 is mapped to 3, or is paired, I guess I should say. So -3 is paired with 5, 0 is paired with 3, 2 is paired with 2, and 4 is paired with -1. So why we know this is a function is if we look at each x value, -3, well, how many y values is -3 paired with? Well, just one. Okay, that's the 5. 0 is paired with just the 3. 2 is paired with just the 2. And 4 is paired with just the -1. Okay, so that's what we mean by each element of the domain is paired with exactly one element of the range. Okay, so this is in fact a function. This mapping over here is also a function. Okay, here we have -1 is mapped to 0. 5 is mapped or paired with 9, and 7 is mapped with 0. Okay. Now you might look at this and say, oh, well, there's two x values both going to 0. This can't be a function. Well, if that's the case, you're thinking of it a little bit backwards, okay? Because what we need is each x value to be paired with exactly one y value. So if we look at -1, how many x values is -1 paired with? Well, or how many y values is -1 paired with? Well, that's 1. We have 0 here, okay? How many y values is 5 paired with? Okay, 1, just 9, okay? And then how many values is 7 paired with? Well, 1, just 0, okay? So we're focusing when we're talking about functions, we're focusing on the x values or the inputs here, okay? Maybe something way we haven't talked about it just yet, but these x values can technically be called inputs. So each input has exactly one output, okay? So like I said, focusing on the x value. So let's actually have a look at an example of something that's not a function, okay? Well, this is not a function. So here we've got -2, 0, and 3 in the domain. And in the y, in the range or the y values are -7, 0, 5, and 9, okay? So if we look, so far so good with the -2. -2 is just paired with -7. And then down here with the 3, that's also fine. 3 is just paired with the 9. But where we run into the trouble here is with this 0, okay? So 0 has two ordered pairs here. That's what these lines mean, okay? So from the last section, relations, okay? 0 is paired with both 0 and 5, okay? So what this means is 0 repeats. Okay, and since 0 repeats, that means this is not a function. So that means if we plug in 0, or if we have 0, that means we're going to get out. Okay, so if we have 0, it's going to be mapped to 0 or 5, or 0 and 5. But once again, with a function, we kind of want to know, okay, if I plug in 0, what am I going to get out? Well, I'm going to get out 0. Okay, you don't want to have to guess and say, if I plug in 0, what do I get out? 0 or 5. Okay, we want to make sure that once we plug something in, we know what we're going to get out. Okay, and that's the main purpose of a function in real life, as we'll see in a couple of examples here in just a bit. Okay, so the big thing to remember about a function is x's can't repeat in functions. If you have a set of ordered pairs, if you have a table, if you have a mapping, if you have a graph, any way you look at a relation, if you ever have an x repeating, then that means you don't have a function. Okay. Once again, we are looking for each x value to be only paired with one y value. Okay. So if you look at the difference between this one and this previous one over here, yes, it's okay if we have two lines coming into a y value. Okay, with a mapping. What we don't want is two arrows or two lines coming out of an x value in a mapping. Okay, so once again, that tells us 0 is paired with both 0 and 5. Over here, we've got -1 is paired with 0 and 7 is paired with 0. Once again, we're focusing on the x here. This x is only paired with one y. This x is only paired with one y. This x is actually paired with two y's, so that means it is not a function. Okay, so x's cannot repeat. So let's go ahead and look at example 1. Okay, so first type of a question you'll see in terms of function is determine if something is a function or not. Okay, and you notice here we've got a mapping and a table. Okay, table's a little bit weird. This is the way they have it in the book, but normally you would see it, vertical. So you'd have the x column and a y column, but same information is being portrayed here. Okay, an x row and a y row. It's just kind of flipped over on its side and flipped around, like flipped over. So once again, a little bit weird, but we can deal with that. But in this case, they say determine whether each relation is a function. Okay, well, this first one, if we go back and look at our examples in that first little bit, this is in fact a function, because if we look at -2, it's just to -3. If we look at 0, it's just to 6. If we look at 3, it's just to 6. And if we look at 4, it's just to 9. Okay, so once again, one way to know if a mapping is a function is look at how many lines are coming out of each x value. If there's just one, that means this is a function. Okay, so this is a function. Let me fix that f a little bit. That looks a little weird. Okay, so it is a function. Well, why is it a function? Well, same as what we just talked about with those other two mappings. Every single x value is mapped or is paired with exactly one y value. Okay, so another way to think about it is there's not two lines or two ordered pairs with the same x coordinate. Okay, so none of the x's repeat. Well, what about this one? Okay, well, if we look at this relation, once again given as a table, which, like I said, looks a little weird, but what we've got here is x's and y's. So this is the domain, this is the range. Now, if we really, really wanted to, and you're really clear about how a function looks with a mapping, what's stopping us from making this table into a mapping? Okay, so if you need to, you can take this table and make it into a mapping, into a graph, into a set of ordered pairs. However you've got to do it, whichever way you feel more comfortable in determining if something is a function or not. Write this as a mapping if you need to. Take it and write it as a mapping, okay? But I'm going to show you as a table, we can tell this is not a function. Okay, and why? Well, look at the x's. We have 1, 3, 5, 1. And as soon as we see that second 1, there's should be alarms going off in our head, okay? But let's look at the y's. 4, 2, 4, -4. We do not care about the y's when it comes to a function. It does not matter what the y's are. The x's are what matters here. So if we look at 1, 1 is paired with 4, but 1 is also paired with -4. So if we had it in a mapping like this, we would have 1 with 2 lines coming out of it, one going to 4, one going to -4. So in this case, we could say 1 repeats. That's why this is not a function, because we have 2 coordinates or 2 ordered pairs where the x value is 1. And once again, that does not make that makes it not a function. Because once again, when we plug in, as we'll see later, when we plug in something, so like if we plug in 1, we just want to get out 4, or we want to get out -4. We don't want to get out both 4 and -4, or 4 or -4. We want to make sure if we plug in 1, we know what we're going to get in terms of we are going to get one single value, okay? Like I said, it'll make more sense, hopefully, when we talk about a real-world example and why a function is important. But just mathematically looking at this is part A is a function because each x value has one line. Once again, that means no repeats in the x's. And the table here for part B is actually not a function because the 1 repeats, okay? So that's looking at it as a mapping in a table. We'll talk about how to do it as a graph here in a second. Ordered pairs is actually probably the easiest because if you just write out all the ordered pairs and you have 2 or more points that have the same x value, then you know it's not a function, okay? But like I said, looking at it as a mapping, looking at it as a table, that's how you tell if it is a function or not, okay? So now that we know what a function is, what it looks like, let's talk about 2 different types of functions, okay? So a function that consists of points that are not connected is called a discrete function. Now, every year in class, I always have people, when they make a mapping like this or make a graph of a relation like this, they always want to try to find some way to connect the points, okay? Well, in this case, if you have a relation like this, you don't know if we can connect the points or not, and that's actually what we're going to talk about in the next example, okay? When we can connect the points, when we can't. So in this case, we're going to talk about a function that is called a discrete function. Well, in math, when we say something is discrete, that means we can count it. Okay? So when we want to say something is discrete, if we want a discrete function, that means we can count the points on the graph. Well, everybody agrees maybe, hopefully, this is a function. If not, go through, write out all the ordered pairs, and you'll see why this is a function. And we'll see why this is a function here in just a bit when we talk about how to tell if a graph is a function very easily, okay? But at this point, take my word for it. This is a function, okay? So if this is a function, well, can we count the points? Well, how many points are there? There's 1, 2, 3, 4, 5, 6, 7, 8. So this is 8 points, not connected. So this means it is discrete. Okay. So once again, discrete in math means you can count it. And if you can count the points here, so once again, kind of looks like scatter shot or something here, or like a scatter plot or something where you just have all the points labeled out, nothing's connecting them. This is discrete because once again, we can count the number of points that are on this graph, okay? Now on the flip side of that, we have a function that is called a continuous function. So a function that can be graphed with an unbroken line or curve is called a continuous function, okay? So in this case, if you want to get technical with it, we have this point here, 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 okay? So you can kind of see we have a bunch of points here, and we can actually go and count a bunch of them, okay? So if you wanted to, you could keep going. There's a point, there's a point. So you can see all these points, okay? Now, if we look at each one of these, we can actually count how many these are, but, okay, what makes this continuous is, well, since these lines are connected, that's telling us, well, what's between these 2 points? Well, there's another point right here. And what's between these 2 points? Well, there's a point right here, and right here, and right here, okay? And right here, and right here, right here, okay? And so on and so on. So what you end up having is, well, look at how many points we have now. Well, at first we had 1, 2, 3, 4, 5, 6, 7, 8. Well, now we should have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. Well, what's to say that there's not a point in between those 2 points and those 2 points and those 2 points? Okay. So what we mean by continuous function is between every point is another point. So even though initially to graph this line or to have this as a graph, we can look at just 8 points. Technically, we could just look at 2 points, okay? But even though you can count the number of labeled points, there's actually an infinite number of points on this line, especially since these arrows go on forever. That tells you it's going on forever. It doesn't end. That means you can keep going out here, and you can see there's infinite number of points, okay? So what this means is there are infinite number of points. And they are connected with the same line or curve. Okay, so what this means is this is continuous. Another way to think about continuous is, can you graph it without picking up your pencil? Okay, so in this case, if we wanted to make this line, we would just draw this line without picking up our pencil. Whereas if we go back to discrete, how would we graph this? Well, we'd have to graph this point. Then we would have to pick up our pencil and move up to this point. And then pick up our pencil and move to this point, and this point, and this point. Once again, a countable number of points, okay? So in this case, we have to pick up our pencil. That means it's discrete. We can count the points. In this case, we can graph the line without picking up our pencil. And once again, even though there's a few different points on here and we can count how many I've got labeled here, okay, between every point, there's another point, okay? So between every point, every 2 points. So let me put that up there. So let me just fix that. Every 2 points is another point. Between every 2 points is another point. So once again, even though we know these 2 points right here are there, well, between those there's another point. And then between those 2 points is another point. And then between those 2 points is another point, okay? So you can kind of see how we can go off to infinity pretty quickly here in trying to count these points. Because once again, there's always a point in between each point, okay? But the big question here is, and what we want to answer is, how do we know to connect the points? So how do we know if we've got something like this, why don't we connect the points, okay? Versus something like this, we can write out these points. How do we know we can actually connect them, okay? And that's what we get into with example 2, okay? In this case, we have a real-world example, and the following example is also going to be a real-world example. So actually showing you why we connect the points instead of just leaving them as random points on a graph, okay? So in this case, we're going to draw graphs. This example has to do with ice sculpting. So what we have here is, at an ice sculpting competition, each sculpture's height was measured to make sure it was within the regulated height range of 0 to 6 feet. Okay, so some wording there. Got to know how to read this. Okay, so what this means, all this means is every single ice sculpture, okay, had to be measured to make sure it was between 0 and 6 feet. Because, for one, does it make sense to have an ice sculpture that is 0 feet tall? Well, no. That would mean it's just flat. You can't really do much with a flat ice sculpture. Okay. On the other side, it can't be more than 6 feet, okay, because whatever the rules of this competition, it's what this word regulated means here, okay? The rules of the competition say it has to be no more than 6 feet, okay? So basically, what they're saying is all the sculpture's heights should be between 0 and 6 feet, okay? Now, it says the measurements were as follows. Team 1 had a sculpture of 4 feet. Team 2 had a sculpture of 4.5 feet. Team 3 had a sculpture of 3.2 feet. Team 4 had a sculpture of 5.1 feet. And Team 5 had a sculpture of 4.8 feet. Okay, so that's all the information we need to know to answer the questions we're going to be asked about this situation, okay? So part A here says, make a table of values showing the relation between the ice sculpting team and the height of their sculpture, okay? So what we need to do here is we need to make a table. I'm going to cheat here and use my neat little tools here for my, so let's see, 1, 2, 3, 4, 5, 6. Okay. And then this way. You make a nice table here so it's easy to read. Okay. So, have a table here. Now, here's the part that we have to be careful of. So, this is going back to last section when we were talking about independent versus dependent variables. Well, what are the two variables we have here? Well, we have a relation between the ice sculpting team and the height of their sculpture. So, in this case, we need to know, well, which one is going to be put where? So, is the team going to be put over here for the independent variable for the x coordinate, or is it going to be the y coordinate or the dependent variable? Okay, so if you remember when we talk about tables, normally it's independent variable on the left, dependent variable on the right. Well, here's where we got to think: which one depends on the other? The height of the sculpture depends on which team sculpted it. Okay, if team 1 sculpted the ice sculpture, we know it's going to be 4 feet, no matter if the people in team 1 were actually team 1 or team 5, okay? There was still, if they sculpted, if those two people or multiple people sculpted the same sculpture, it would be 4 feet, okay? So not to confuse anybody here, but what that means is as long as team 1 did the sculpture, it was going to be 4 feet, okay? So the height of the sculpture depends on which team sculpted it, okay? So in this case, height would be our dependent variable, which is in feet, because it depends on the team number. Okay. Now, once again, flip that around if you're unsure. Does the team number depend on the height of the sculpture? Well, in this case, you wouldn't even know the team numbers unless they were in the competition. So the height of their sculpture isn't affected by what team number they are, okay? But the height of the sculpture does depend on which team number sculpted it, okay? So what we have here is we have a table where the team numbers are the independent variables and the height, or the team number is the independent variable and the height is the dependent variable. So all we got to do is read the data. So in this case, team number 1 had a height of 4 feet, okay? Team number 2 had a height of 4.5 feet. Team number 3 had a height of 3.2 feet. Team number 4 had a height of 5.1 feet. And team number 5 had a height of 4.8 feet. Okay? And that's actually it. That's all we got to do to make this table. Okay? But the big thing here is the team number is the independent variable. and the height is the dependent. So let me find a better way to write that. Is the dependent. So let me do it this way. Keep it on the page here. Because once again, the height depends on the team number. Okay. So that's why we have the team number is on the left column and the height is in the right column. Okay. So that's it. We made the table. So that means team number 1 had a height of 4 feet, team number 2, 4.5, team 3, 3.2, team 4, 5.1, team 5, 4.8. Okay. So let's go on to the next question. State the domain and range of the relation and then determine whether it is a function. Okay. So what we've got to do here is, and just by the sake of the problem here, I've kind of had to I'm going to have to switch back and forth here, but once you have these in your notes or you have this, you can see the table at the same time, okay? But if we go back to our table, well, the domain is just going to be all of the values for the independent variable, the x values, okay? So when we want the domain, well, what is the domain in this case? Well, it's going to be the team numbers. So it's going to be 1, 2, 3, 4, and 5. But here's a place where, once again, if you weren't paying attention very much or you've forgotten a little bit from last section, when we write out the domain, we have to include braces, okay? If we don't include braces, you've just made a list of numbers. The braces tell us all these things, all these numbers have something in common. And what all these numbers have in common, these are the team numbers, okay? So once again, this is telling you how many teams there are essentially. So you've got team number 1, team number 2, team number 3, team number 4, team number 5. On the other hand, for the range, okay, it's going to be the other column. So if we go back and look, that's just the heights of all the sculptures, okay? So we have a height of 4, a height of 4.5, a height of 3.2, a height of 5.1, and a height of 4.8. So in this case, it's going to be, once again, domain and range have to be in braces. It's going to be, so let me get it on my paper here, because once again, that's the difficulty of having something on different pages here, okay? The domain is going to be 4, 4.5, 3.2, 5.1, and 4.8, which once again, this corresponds to the height. And once again, definitions of domain and range. Domain has all of the independent variables, the values for the independent variables, which are the team numbers. The range has the values of all the dependent variables, or in this case, the height. Okay. So with this being said, looking at this table, is this a function or not? Okay. Once again, if we need to, go back and look at the table. Also, if we need to, make a mapping out of this, list out the ordered pairs, however you need to do it to tell if it's a function, do it. Now, from a table, we can see very clearly this is a function, because do we have any repeating team numbers? Okay. Well, no. Every team is differently labeled, and that makes sense in real life, right? We don't want 2 teams labeled team number 1, because then when I said, okay, team number 1 had a height of 4 feet, well, which team number 1 were you talking about? Okay. That's why in sports, most players have different numbers, because if you had 2 people with the same number playing at the same time, how are you going to tell which one's which? Okay. So that's why, once again, functions are important in real life, because in real life, do we want 2 teams, team number 1? Do we want 2 team number 2s? Do we want 2 teams of number 3? Okay. So in this case, this is a function. And logically, it should make sense why this is a function. Once again, you can't have more than one of each team number. Okay, so once again, what I'm talking about there is we do not want two teams that are number 1. We don't want two teams that are number 5. We want this to be a function, so that way when we look at team 1, well, you know what I'm talking about. I'm talking about team 1, and they had a sculpture of 4 feet. If we called both team 1 and team 5 both 1, well, then we would have team 1 with a sculpture of 4 feet and team 1 with a sculpture of 4.8 feet. Okay? Does that make sense in this situation for this competition? Well, not really, because that's why we want team numbers to be different. Okay, so that's what makes this a function in real life. Okay. Now, part C, if we've got the table and we've got the domain and range, the graph should be pretty easy. Okay, but first off, we need to write this. So let's read the whole question here. Write the data as a set of ordered pairs, then graph the data. Well, once again, we see this word set. Okay. So if we see this word set, we know we're dealing with a relation or domain and range. So we got to use braces. Okay. So let me draw a better set of braces here. So braces. Well, what are all the ordered pairs? Well, the ordered pairs are given by the table. Okay. So the columns or the rows in the table. So the first ordered pair we're going to have is team number 1 had a height of 4 feet. X comma Y, independent variable, dependent variable. Okay. 1, 4. The second ordered pair is 2, 4.5. The third ordered pair is 3, 3.2. The third ordered pair is 4, 5.1. And the last ordered pair is 5 and then 4.8. So let me get rid of that little dot right there. So this relation has 5 points. Okay. And once again, these points come directly from the table. Okay. And honestly, from the very beginning, we could have taken this and made the ordered pairs. But the big thing is we got to remember which is the independent variable versus which is the dependent variable. Okay. So once again, that kind of plays a role here because it tells us which is going to be our x value, which is going to be our y value. Okay. Now, in knowing that, now we know what our axes need to be for our graph. Okay. So if you look here, we've just got what we call the first quadrant. Okay. Because a lot of things in real life, and to make this point here is, does it make sense for us to have a negative team number? Does it make sense for us to have a negative height? Okay, so in this case, we're starting both of these at 0. We don't continue the axes down. Okay, so that's why you only see this little block right here. And the other reason we see this little block is, well, we don't technically need to go higher than 6 because every single sculpture should have a height of less than 6 or 6 or less. Okay, same thing. We shouldn't have a higher team number than 5 because we only see that there's 5 teams competing. So we don't have to go to team 6, team 7, team 8, team 9. Okay, so once again, we're only concerned with positive numbers on both the x-axis and the y-axis. Okay, but that's exactly what we need to do. Is the x-axis, well, it's corresponding to the team numbers. Okay, so I labeled out here 1, 2, 3, 4, 5. And the y-axis has to do with the heights. So those are the y coordinates, 4, 4.5, 3.2, 5.1, and 4.8. In this case, it's up to you how you want to label it, but I just labeled it. I had enough space here that I labeled it by 1. So 1, 2, 3, 4, 5, 6, 7. And technically, we didn't even need to go to the 7, but it doesn't hurt us to go that far because we know all the sculptures have to be 6 feet or less. Okay, so technically we could have stopped there at 6, so we could have drawn a line right here and just made it 6. But once again, doesn't really matter. We've added an extra height there. Okay, but what we need to be focused on now is once we have everything, our axes labeled and everything, just plot these points. So we know. So what this tells us, the point 1, 4 tells us we have team number 1, and their sculpture had a height of 4. Okay. Team number 2 had a height of 4.5. Team number 3 had a height of 3.2, so it's going to be above 3 a little bit, okay, just a little bit, so not quite half, so it's like half of half almost, so it's like right here. And then team 4 had a height of 5.1, so we go to 5 and a little bit further, so it's like right there. And then lastly, team 5 had a height of 4.8, so we go to 4, and we go between 4 and 5, but it's actually a little bit closer to 5 than it's closer to 5 than 4, so that means we're going to be somewhere like right here. Now, here's where we can kind of see, do we connect these dots? Okay. Do we connect these dots? Well, in this case, we do not connect these dots. Okay. Do not connect the points. Well, why don't we connect the points? Well, if we connected these 2 points right here, that would mean that we're representing, so if we draw a line here, that means there's a point in between these 2 points. Well, can we have a team number of 1.5? Well, no, we can't have a team number of 1.5. Okay? Because there's a countable number of teams. So there's 1, 2, 3, 4, 5 teams. There's not an infinite number of teams, because if we drew the line here, then we would saying, oh, there's a team 1.1 and a team 1.2 and a team 1.3 and a team 1.11 and a team 1.12 and a team 1.13. Okay, so you're saying there's an infinite number of teams. Well, we don't have an infinite number of teams. We have a countable number of teams. Okay, so do not connect the points, because we can count the teams. Okay, so how we know we can connect the points or not? Well, we can't in this case, because once again, if we connected these points in any way, that would tell us that we had an infinite number of teams or an infinite number of ice sculptures, which neither of those things are true here. Okay, we do not have an infinite number of teams or an infinite number of ice sculptures. Okay, so once again, this is the graph, and that's it. Okay, so we graph the data, because once again, we do not connect the points because we can count the number of teams. Okay, and that's the difference, and that's actually going to answer our next question. Okay, so if we don't connect the points because we can count the teams, well, is this relation discrete or continuous? Well, look at the graph. Can I count how many points are on this graph? Can I count how many teams there are? Can I count how many sculptures there are? Well, yes, there's 1, 2, 3, 4, 5 teams, 5 sculptures. Okay, so this is actually discrete. Okay, and it's discrete because we can count the number of teams and sculptures. And why can we count the number of teams and sculptures? Well, once again, that goes back to us not connecting the points, because we only have one team 1, and they only have one sculpture that is 4 feet. We only have one team 2. They only have one sculpture that is 4.5 feet. Okay, so this would be considered a discrete situation, meaning we can count the number of sculptures and we can count the number of teams. Okay, so that means, for the answer to part D, this is discrete. Okay, now that was a long example, I know, but let's do another one. Okay, so this is an extra example. So an extra example number 2, I'm going to give you a similar situation, except for we're going to see the difference between discrete and continuous, okay? So what I mean by that is, in this example, we have a bird feeder will hold up to 3 quarts of seed. The feeder weighs 2.3 pounds when empty, which that means there's 0 quarts, so if it's empty, there's 0 quarts of birdseed, and 13.4 pounds when full, okay? So that means if it holds up to 3 quarts, that means if it's full, it has 3 quarts. So in this case, they want us to make a table that shows the bird feeder with 0, 1, 2, and 3 quarts of seed in it, weighing 2.3, 6, 9.7, and 13.4 pounds, respectively. So before we make this table, we need to know, what does this word respectively mean? Okay, well, if you have, so just to tell you, all right, nobody here to answer this question, but you can answer it in your head. But what it means respectively means, what it means to be respective in this case is, if you see this list here, we have 0, 1, 2, and 3. Well, in this list, we have 2.3, 6, 9.7, and 13.4. What this word respectively means that each place in the list matches up. So that means 0 matches with 2.3, 1 matches with 6, 2 matches with 9.7, and 3 matches with 13.4. Okay. So in this case, we've got 4 values for number of quarts of seeds and 4 values for the number of weights. Okay. And once again, this word respectively means 0 goes with 2.3, 1 with 6, 2 with 9.7, and 3 with 13.4. So to make a table of this, once again, let me pull out my fancy tools here. So in this case, let's see, 1, 2, 3, 4, 5. 5. Let's go right in the middle here. 1, 2, 3, 4. Oh, which I did not split that in half, so I need to make this a little bit longer. Oops. Okay. So here's our table. Now we need to figure out how we're going to label this and what numbers we're going to put where, okay? But once again, we need to think which is the independent variable, which is the dependent variable. So if you think to yourself in your head, well, do the amount of birdseed, does that depend on what the weight is? Okay, well, no. The weight, the weight, forgot to change it back to pen. The weight actually depends, once again, weight in pounds, it depends on how much bird seed you put in. So amount of seed, and this is in quarts. Okay, so once again, we need to know the amount of seed is actually the independent variable. And just like last section, if you need to know which is independent, which is dependent, use that word depends, okay? If one depends on the other, then you know which is the dependent variable, which makes the other one the independent variable, okay? So weight depends on how much seed you put in it, so how amount of seed in the bird feeder, okay? So that's why amount of seed is on the left being the independent variable or the x variable, and the weight is on the right being the dependent variable or the y variable. Okay, once again, it's the difference between x and y. Okay. So now that we've got that out of the way, well, now what do we do to make this table? Well, we just make the rows. Okay, so if we have 0 quarts of seed, how much does the feeder weigh? Well, it tells us here in this list, 0 corresponds to 2.3 pounds. It also tells us up here, when it's empty, it weighs 2.3 pounds, okay? Well, how much does it weigh when there's 1 quart of seed in it? Well, it would weigh 6 pounds. And it's definitely not a 6. 6 pounds, okay? Same thing, 2 quarts of seed tell us that we would have 9.7 pounds. And lastly, 3 quarts, or when it's full, tells us we have 13.4 pounds. Okay, So if there's 3 quarts of seed, it weighs 13.4 pounds. Now, do we need to go any further? Can we have 4 quarts of seed, 5 quarts of seed? Well, no. Once again, if it's full, it's at 3 quarts of seeds. Up to 3 quarts, that means it's full, okay? So we can't put any more points on here going beyond 3, okay? But that's actually, based on the data we have here, that's our table, and that's it, okay? We just have to remember the left column is always our independent variable. The right column is always our dependent variable. And that's the tricky part of making a table on these real-world situations is we got to figure out which is the independent variable and which is the dependent variable, okay? But other than that, table's pretty easy. That's the table, okay? Now let's go ahead and answer the second question. So just like the last example, the second question is state the domain and range of the relation, okay? And then determine whether it is a function, okay? Well, once again, if we've got the table made out, it's pretty easy to tell what the domain and range is. The domain is going to be the amount of seed. So what amounts of seed do we have, okay? So that means the domain is going to be, once again, with the braces, it's going to be 0, 1, 2, and 3. Okay, based on the data we have, that is the domain. 0, 1, 2, 3. And once again, we've got to use braces here because the domain is a set, and these braces tell us, well, what is this? This is the amounts of seed in quarts. So how many quarts of seed we have. Okay, that's what these braces mean. That means everything here has something in common. That means these are the amount of seed in quarts. Well, the same thing happens with the range. The range in this case, well, if the domain is the amount of seeds in quarts, so all the values we have there, well, then the range is going to be 2.3, 6, 9.7, and 13.4. So in this case, 2.3, 6, 9.7, and 13.4. And what do these braces tell us? Well, these are all the weights of the feeder. Okay. So once again, domain and range, if you have the tables, pretty easy. Just make sure there's no repeats in when you're talking about domain and range in terms of x's or y's, okay? But since we didn't repeat anything, that actually immediately tells us that this, once again, just like the last example, this is a function. Now let's logically think about why this is a function. If I put a different amount of seed in, am I ever going to get the same amount of weight? So, another way to think about that is if I put one amount of seed in, so if I put 1 quart of seed, can it weigh both 6 pounds and 2.3 pounds? Or can it weigh both 6 pounds and 9.7 pounds? Well, no, that doesn't make any sense. If you put 1 quart of seed in, you would expect it to always weigh 6 pounds, okay? You kind of break the laws of physics if you said 1 quart of seed weighed 6 pounds and 13.4 pounds. Or you would say 1 quart of seed weighed 2.3 pounds and 9.7 pounds, okay? So this necessarily has to be a function, okay? And why is that? Well, different amounts of seed give different weights. Okay, so once again, every single amount of seed that you put in is corresponding to a different weight. Once again, if you put in 0 seeds, 0 amount of seeds, so 0 quarts of seed, the weight's going to be 2.3. If you put in 1 quart of seed, the weight's going to be 6, 2, 9.7, 3, 13.7. Once again, you don't have 3 quarts of seed weighing both 13.7, or actually, it's a little bit of a typo there. Or righto, I guess you could call it. That should actually be 13.4. So that is my bad. Kudos to you if you caught that. Okay. So glad I caught it before I actually published the video. But anyways, once again, this is a function because different, okay, amounts of seed correspond to different weights. Okay. So pretty straightforward there. Now let's look at, and this is the main part of this this example is let's write the data as a set of ordered pairs, then graph. Okay. Well, once again, it all stems back from us doing the table correctly. If we did the table correctly, then we have the ordered pairs right there for us to graph. Okay. So what are the ordered pairs? Well, once again, set of ordered pairs. So set here, we have 0, 2.3. We have 1, 6. We have 2, 9.7. And we have 3, 13.4. Now, same thing as last time. Does it make sense for us to have negative amounts of seed? Can we have a negative quart of seed? Well, no. Can we have a negative weight? Okay, well, no, we can't have a negative weight either. So it only makes sense for both our x coordinates and our y coordinates to be positive, and that means we're in this what we call quadrant 1. Okay, meaning that the amounts of seeds and the weights are all positive, which once again in this real world situation makes sense. Okay, we don't want negative weights or we don't want negative amounts of seed. Okay, so now what do we do? Well, if we have the x-axis, the independent variable, amounts of seed, y-axis is the dependent variable or the weight, all we got to do is go in and say, well, 0. Well, how much weight did we have when we had 0 in it? 0 quarts of seed. Well, we had 2.3, so it's going to be somewhere like right there. Okay. Well, what happens when we have 1 quart of seed? Well, it is 6. Okay, the weight is 6. When we have 2 quarts of seed, the weight is going to be 9.7. So we're going to be somewhere like right here. And then 3 quarts of seed give us 13.4. So 13.4 going to be roughly like right there. Once again, drawing this by hand is not going to be perfect. But what we see here is we have 4 points. Okay. But here's where we answer the question. Do we connect the points? Okay. In this case, we connect the points. Okay, well, why do we connect the points? Well, think about this very logically. If I have 0 quarts of seed and I have 1 quarts of seed, well, couldn't I cut that in half? Couldn't I only put 1/2 quart of seed? Okay, couldn't I put half a quart of seed in there? Well, yeah, I could. Could I put 1.2 quarts of seed in there? Could I put 1.5 quarts of seed in there? Could I put 2.9 quarts of seed in there? Okay. So once again, here we can put different values for quarts. Okay. So we can actually put amounts of quarts in between 0 and 1. Same thing on the y-axis. Can we have a weight that is between 2.3 and 6? Well, depending on how much seed we put in, yeah, we can. If we had half a cup of seed, we should have, roughly, it's looking like 4.5, okay? 4.5 pounds of weight, okay? But how we can figure that out is, once again, we connect the points. Once again, the whole reason why we connect the points, I actually did pretty good there. Okay. So the reason why we connect the points is, well, we can have the amounts between 0 and 1. We can have the amounts between 0 and 2 and 2 and 3. Same thing, we can have the amounts between 2.3 9.3 and 6. We can have the amounts between 6 and 9.7, and then 9.7 and 13.4. So if you look at this, if we had this point right here, that would tell us, okay, we had 1.5 quarts. That's like 7.7, okay, or 7.8, or 7.9 even, somewhere around there. It's close to 8, but not quite 8, okay? But once again, the reason we connect the points is there are points in between each one of those points, okay? So why do we connect the points? Because, which I forgot to change it again to the drawing implement, okay? So in this case, we can put other amounts of, don't know what that little tail on the O there is for, but we can put other amounts of seed to get different weights. So once again, we're not stuck. We don't have to put just a quart of seed in, okay? We don't have to put just 2 quarts of seed in. We could put 1.5 quarts, okay? We could put 2.5 quarts. We can put 2.7 quarts. We can put 1.6 quarts. We can put 1.33333, 1.3 repeating quarts, okay? So once again, we can have all these different values. That means we connect the points. Okay. Now, since we connect the points, well, what does that tell us? Well, we used one straight line. Okay. In this case, it's a line, but one curve, I guess you could say, if it was curved a little bit. But we used one straight line to get all the points on it. So when we answer part D, is the relation discrete or continuous? Well, can we count all the points on this graph? Well, we used 4 to make the graph. Okay. So that's how many we used to plot the points to graph it. Well, that doesn't tell you all the points that are on the graph. Once again, what about if you throw 2.5 quarts of seed in there, or 1.5 quarts of seed, okay, or 0.5 quarts of seed? That's the thing. Since we can have all of the different weights and all of the different amounts of seed, that means all these are connected. So that means there are an infinite amount of points. And since we connected it all with a straight line, this is continuous. Okay. Well, why is it continuous? Well, once again, you connect all points with a single line. Okay. In this case, that single line also gives you a bunch of other points which you cannot count. You cannot count how many points there are. So in this case, you have infinite amount of points. Okay, so this idea of discrete or continuous, it can get kind of tricky and messy, but we'll practice with this, so don't worry about that. But once again, I wanted to show you the difference. So if you need to, go back through and see the difference in the two questions, one being discrete, one being continuous. One telling us why we can't connect the points, while the other one telling us why we can connect the points, okay? So if you're unsure about why we can, so going back to this right here, how do we know to connect the points? Well, once again, it depends on if it's discrete or continuous, okay? So like I said, we'll practice a little more with that, the difference between discrete and continuous, and seeing it in terms of real world examples, okay? But let's go ahead and go on to the next part of the notes, okay? So like I said, this is going to be a pretty long video. We're about halfway through the notes now. But with that being said, let's go on to the next slide here. Now, we've looked at how we can tell if a table is a function. A mapping is a function. We can tell easily by the ordered pairs if it's a function or not. You can actually kind of tell by the domain and range if you know what you're looking for, okay? But now let's talk about if you have a graph. So if you have a graph of a relation, okay, so once again, what we just did, we graphed a relation, whether discrete or continuous, so both in those cases, whether it's discrete and has just a bunch of points, or if it's continuous and has a line, okay, you can tell if it is a function or not by using what we call the vertical line test, otherwise known as either the VLT or the pencil test, okay? So vertical line test, everybody hopefully at this point knows what a vertical line is. Vertical line is a line that goes straight and down. That's why we call this the vertical axis or the y-axis, the vertical axis, okay? But what the vertical line test tells us is if a vertical line intersects the graph of a relation more than once, the relation is not a function, okay? So what do we mean by that? Well, if we graph the relation, so let's look at this first graph here. If we graph this relation, okay, in this case it's a relation, you can see it's actually a continuous relation, a continuous, I guess you call it a relation at this point. Well, we can tell, is it a function or not? Well, let's draw a vertical line right here. If we draw a vertical line right here, we only cross the graph one time, okay? What happens if I draw a vertical line right here? We only cross the graph one time. What about right here? One time. One time. Okay. So what we've got here is if we think of this vertical line as moving, if we can move this vertical line and it only crosses the graph at one point every single time, that means it is a function. So this is actually a function. Okay. Well, let's take a look at this next one. Well, we can draw a vertical line right here, right on the y-axis, and it only crosses one time, okay? But what about this line right here? What happens when we draw it? Well, it actually crosses the graph twice, okay? So if you can draw one single line, okay, so if a vertical line intersects the graph more than once, well, this is what's happening here. This is not a function. And it only takes that one time to see. Even though we drew one over here that passed through it only one time, okay, we can draw at least one line that passes through it more than once, okay? Now, what this means, and you might be thinking, well, what does vertical lines have to do with x's not repeating? Well, think of what each vertical line represents. If we come here and we cross this point, this line right here, or cross the graph right here, well, what x value is that? Okay, well, let's say it's -3 or something, okay? Well, that tells us there's only one point with the x value of -3. And if you can do that with any other vertical line that you can write down, well, what that means is every single one of your x values is unique, okay? That means you don't have an x value that repeats. Now, if you look over here and you look at this line, well, what happened here? We drew the line and it crossed two times. That means we have 2 points, one right here and one right here, that have the same x value, okay? So that means we have 2 points in our relation that the x value repeats itself, okay? Or if you look at the mapping, that means we have the same x value having 2 lines coming from it, meaning we have it going, the x being mapped or paired with this y value, and the x being mapped and paired with this y value, okay? So that's why the vertical line test tells us if it's a function or not. So once again, what it is if you can draw a vertical line anywhere and hit the graph more than once, then it's not a function, okay? Now this one is a unique example here, another one from the book though. If we look at this one, this is also actually a function. But the reason I wanted to talk about this one in particular is, well, once again, we can draw as many vertical lines as we want here, okay? Not too vertical there. But once again, as many vertical lines as we want, we're only ever going to hit the graph once every time. Now you might say, well, what about right here? What if I draw a line straight down through here? Well, it's actually only going to hit the graph right here, not here. That's what that open circle means. If you remember anything about inequalities, well, what did the open circle mean and what did the closed circle mean? Well, the open circle means that it was not equal to that point. The closed circle means it is equal to that point. So if we look at this one, it passes through this open point, but then it hits this closed point. So this is a function. But the reason I wanted to show you this is an example of a function that is not discrete, nor is it continuous. Okay, so what do I mean by that? Well, can you count the number of points on this graph? Well, no. Okay, so it's not discrete. Can you graph this line without, or graph this relation without, or function without lifting your pencil? Well, no. If you go through here, oh, I got to stop because I got to pick up my pencil and come down here and finish the line. Okay, so just a neat little example here that they threw at you in the book. This is actually an example of a function that is neither discrete nor continuous. Okay, so not really going to be checked on. This is more higher level stuff here, but just to show you that there are functions out there that are not discrete and are not continuous. This is an example of one of them, though. But once again, it is a function because it passes what we call the vertical line test or the pencil test. Now, the reason they call it a pencil test is think about each one of these vertical lines as a pencil straight up and down. If you move that pencil from left to right, how many times does it hit the graph? Well, if you keep moving it left to right, well, it's hitting it once. It's always going to hit it once, always going to hit it once, always going to hit it once. Whereas here, if you move the pencil from left to right, not hitting it, it's going to hit it once. But then from here on out, it's going to hit the graph twice. It's going to hit it every single time you draw a vertical line. Okay, so this means it's not a function. This is a function. Okay. So let's go ahead and look at example 3. Now, in this example, I am going to be using Desmos. So if you've got the link to Desmos on your Chromebook, you probably want to open that up if you want to follow along with this example, because I'm going to show you how to tell if an equation is a function or not, okay, by using Desmos. Now, what I mean by that is, well, let's open Desmos, okay. Well, Desmos is a graphing calculator here, okay. And what we can do with it is if we know the equation of a function or in this case, know the equation of anything, if we graph it, we can actually tell if it's a function or not, okay? So when we look at the question here, determine whether negative 3x plus y equals 8 is a function, well, we can graph it and use the vertical line test to tell if it's a function or not, okay? And this Desmos calculator makes it really easy because all we've got to do is go into Desmos and type in negative 3x plus y is equal to 8. As you can see, we get this line here, okay? It actually does a nice job in plotting the line. You could see a bunch of different points on here, so you can hover over it and click on it. And you can see this point right here is the point negative 2, 2. You can keep going down and you can see all these other points, but you can see this point right here is the point negative 4, negative 4. Okay. You can zoom out, so you can zoom in or zoom out. Okay. Well, you can see this point right here. Well, let's zoom in a little bit. See this point right here is well, zoom in a little bit more. See this point right here is 420. Okay. So you can actually zoom around, pan around a lot, okay? Just by typing in the equation, it graphs it for you, okay? You can see this point right here is 0, 8, okay? So you can see all sorts of different points here. Now, the graph does, if you go back home, it will, in this case, if you hover over it, it'll tell you what your x-axis, or your x, what we're going to call x-intercept and y-intercept, which is something we'll learn about later, but it'll tell you these points where it crosses each axis, okay, which that's very important. But the whole point in this is, once again, no matter how far you zoom out, how far you zoom in, if you look at this line, how can we tell if it's a function or not? Okay, well, once again, by looking at the points, looking at the graph, we can draw vertical lines. Okay, so if we can draw a vertical line anywhere here, we're ever only going to cross the graph once. Okay, so if we go back here, so let me get a couple points here just so we can actually graph this. So what do we say? Negative 2, 2, and negative 1, 5. Let's do those 2 points. Okay, so negative 2, 2. So in this case, negative 2, 1, 2, 2. So we got this point right here. And we have negative 1, 1, 2, 3, 4, 5. That's really all we need to graph this point or graph this equation. I'm going to cheat here and use my little nice little tool here. So what we've got is we've got a line going like this. Well, there we go. That looks a little better. But once again, even though it's kind of steep here on the graph that I've chosen, that I've drawn here, once again, we cannot find a vertical line where it will cross more than once. So once again, we have it crossing the graph once here, once. Okay, you can see the y-axis kind of acts as a vertical line. We only cross it once. Okay, so this is in fact a function. And we will talk more about graphing. So we'll talk more about graphing in chapter 3. That's where we really get into graphing equations and functions and everything, okay, by graphing by hand and then also doing some tricks on the graphing calculator. But I just wanted to show you, if you are given an equation and you want to know if it's a function or not, graph it, okay? And like I said, give you access to Desmos, the calculator here. All you got to do is type it in and it will graph it for you. And then you can zoom in, zoom out. Okay, so zoom out, zoom in. If you hit this home button, it'll take you right back to the 10 by 10, or I guess in this case, 10 by 7 or 10 by 8 grid. Okay. But once again, zooming in and zooming out, you can see this graph will never have an instance where you can draw a vertical line and it hit the graph more than once. So once again, this is a function. Okay. And once again, we will talk more about graphing. So we will graph more in chapter 3. Okay. So if you're not understanding what I mean by graphing here, I'm just kind of giving you a free little hint here is you can use Desmos graph, and then based on what the graph looks like, you can tell whether it's a function or not by doing the vertical line test. Okay. So what we've learned with this is a function can be represented all the ways a normal relation can. So we can represent it as a table, a graph, a mapping, just like we saw in those 2 middle examples. And then now we know it can be represented by an equation. Okay. So in this case, if we have an equation, we can tell if it's a function or not by graphing it. Okay. And there's other ways we can tell, but like I said, we'll get more into that when we get into the graphing section to tell if an equation is a function or not. But like I said, if you can graph it, you can always use the vertical line test. But also at the same time, if you can make a table, you can make a mapping, then you can also see if it's a function or not by looking at the table and mapping, okay? So basically what this is saying is if you know what the table is, you can make the graph, okay? If you know what the table is, you can make the mapping. If you know what the mapping is, you can make the graph. If you know what the mapping is, you can make the table, okay, and all this. But now we're going to get to a point, and we're not going to expressly talk about it in this section, but we're going to get to a point where if we know what the graph looks like, we can tell what the equation is. Or if we know what the equation is, we can tell what the table would look like. Or we can tell what the mapping would look like. But what I want you to focus on right now in terms of equations is if you want to know if equation is a function or not, graph it and see if it passes the vertical line test. And then we'll talk later more about other ways we can tell if an equation is a function or not, okay? So the last thing that we've got to talk about in our notes is what we call function notation, okay? So function notation is a way we can write an equation to let us know that the equation we have is actually a function, okay? And it also allows us to tell more about the equation in terms of makes it easier for us to get ordered pairs out of it, okay? So what I mean by that is if we know an equation is a function, so just like that last one, if we know the equation is a function, we can write it in function notation, okay? Well, what is function notation? Well, first off, you need to solve the equation for the dependent variable, in this case the y variable, before putting it in function notation. Now, we'll talk more about this next chapter. We haven't talked about solving equations for different variables and things like that, but just so you kind of know where we're going with this is if you want to put it in function notation, in this case, you've got to be able to solve for y. So I do that here. If you don't understand how I'm doing this, that's something we're going to talk about in the next section. But once you have solved it for y, all you do to write your equation in function notation is you replace the y with f of x, okay? So what this means is we have a function of x. That means we have a function of the independent variable. So what that means is if we have y is equal to 3x plus 8, once we put it in function notation, the only thing that changes is instead of y, we're going to put f of x is equal to 3x plus 8, okay? So once again, if you've got it, you got to solve it for y, which like I said, we're going to talk about that in chapter 2, how to solve equations for y. So like I said, if you're having trouble understanding with what I'm doing right here, that's nothing to be worried about because we're definitely going to address this. We got to know how to do this for a lot of stuff that we're going to do later, okay? So if you're unsure what you're doing here, once again, just know that once you solve for y, you get it in terms of y is equal to 3x plus 8. Well, all you got to do is take the y and replace it with what we're calling f of x, okay? So f of x, the function of x, f of x, okay? And once again, this tells us y is equal to f of x. Well, what does this even do, okay? Well, this allows us to say, well, if we have f of x is equal to 3x plus 8, and we know x is equal to 5, we can then say f of 5. So we put the 5 into the function notation, and when we do the order of operations, when we plug in 5, it'll tell us what f of x is or f of 5 is, which means when you plug in x is equal to 5, y would be f of 5, which is 23, okay? So what this allows us to do is if we know the input or the x value is 5, the y value is going to be 23. So it's an easy way for us to tell, well, if we have this function, what's our ordered pair going to be? Well, it's going to be the x coordinate is 5 and the y coordinate is 23, okay? So once again, way function notation works is it kind of makes it easier for us to tell ordered pairs, which once again, if we talk about relations and functions, it all centers around ordered pairs. So what we have here, we plug in 5, that means we're going to get out 23, okay? That means when we plug in, so if we have an x, our y is 23. So that gives us the ordered pair 5, 23, okay? So let's look at a couple of examples on this. Okay, so example number 4, function values, okay? Well, what are we doing here? Well, in this case, we're given a function. We're saying f of x is equal to negative 4x plus 7. Find each of these values, okay? So we have function notation here, but once again, we can think of it as this just being y is equal to negative 4x plus 7. So when we see this written as f of 2, okay, all it's asking us is what is the y value when x is equal to 2, okay? So if x is equal to 2, then all we got to do is take this 2 and plug it in for every x in our equation, okay? So when we do that, we get negative 4 times 2 plus 7. Order of operations kick in, so negative 4 times 2 is negative 8. Negative 8 plus 7 is negative 1. Okay, so what this means for us is f of 2 is equal to negative 1, which means x is equal to 2, y is equal to negative 1. So that gives us the ordered pair 2, negative 1. Okay, so like I said, function notation, not much different than solving other equations and things like that, which, like I said, that's something we'll talk about next section, but all we're really using here is our ability to do order of operations. If we know what the variable is on the inside here, so x, then whatever is placed in there, so the 2, that's what we plug in for every x, okay? So if we look over at part B, this one gets a little bit more tricky, but we have f of negative 3 plus 1. Well, what this tells us is we need to do f of negative 3 first, then add 1. So you can kind of think of it as kind of like order of operations. We always do what's here first, then we do what's on the outside of the function, okay? So f of negative 3 plus 1 means we've got to do f of negative 3, kind of like we did over here, and then once we get what that is, add 1 to it. So all that means is we take negative 3, plug it into our function. So negative 4 times negative 3 plus 7. Once again, we've got to do all that, then add 1. So that's why I use the parentheses here, okay? Well, what's negative 4 times negative 3? Well, that's 12. We still have the plus 7. What's 12 plus 7? 19. What's 19? And then finally plus 1, that's 20. So what that means is f of negative 3 plus 1 is equal to 20. So that means when x is equal to negative 3, y plus 1 is equal to 20, okay? Which then you can go and say, well, if y plus 1 is equal to 20, that means y is equal to 19. So when f of x, or so f is negative 3, then y is 19, okay? So this would technically give you the ordered pair negative 3, 19, okay? And then once again, plus 1 tells us 20. So once again, if you add 1 to the y, that gives you 20. And that's going to be something we talk about a little bit later when we get more into graphing functions and things like that, okay? But like I said, in finding the value, that's what we're looking for. We're looking for what it is once you do all the calculations, okay? So plug in your negative 3, figure out what f of negative 3 is first, then add 1, okay? Example 5, same kind of thing here, except for they talk about nonlinear functions, which is something we'll talk about later on in the year, okay? So later on when we talk about graphing equations and graphing functions, when it says nonlinear, that means when you graph it, you just don't get a line, okay? You get actually like a curve or something, okay? But nonlinear function values, they tell you if h of t, so in this case they're calling the function h, so h and then the independent variable is t, so h of t is equal to negative 16t squared plus 68t plus 2, find each value, okay? So once again, we're plugging in h of 4, means we're taking our function, so what we have up here, and instead of having t in every place, we're going to have a 4. So we take this 4 and we put it in the place of t. Now, just like we've done before in previous sections, whenever I plug into a value or plug into an expression, I always use parentheses. So in this case with the 4, I'm going to put parentheses around it so it's 4 squared. Here I know it's 68 times 4, okay? So then when I do this, order of operation kicks in, so exponents, 16, okay? Everything else stays the same. Then we do multiplication. Negative 16 times 16 is negative 256. Leave everything else the same. 68 times 4 is 272. Leave everything else the same. Then we have all addition, so we work from left to right. So negative 256 plus 272 is 16. We still have the plus 2. So we get out 18. Now this is a lot of steps here, but It's just order of operations, okay? So when you're doing function values, it's pretty much just order of operations, okay? So once again, we plug in 4, we get out 18. So that means if h of 4 is equal to 18, that means you have the ordered pair for 18. Okay, so the t is 4, and in this case I say y, but it could be h, it could be whatever variable. They're just telling you the dependent variable is 18. So you have the ordered pair for 18. Okay. Now part B, this is a little bit tricky. In this case, you have on the inside h of g, and then you have brackets around it saying you're multiplying that times 2. Well, all you're saying here is we're taking 2 and we're going to distribute the 2 on what we're calling h of g. Well, what is h of g? We know what h of t is. If we go back, h of t is this. Well, what's h of g going to be? Well, it's going to be the same exact formula, or same exact equation, or same exact function, except instead of t in every place, we're going to put a g. So kind of like I did with the 4, if I'm plugging in g in every spot, I'm going to put parentheses around it, okay? And once again, that means we have g squared, 68g, plus 2. Since these are variables, we can't actually multiply this or add this. There's no like terms. So all we got to do is we got to distribute the 2, okay? So 2 times negative 16, 2 times 68, 2 times 2. So when we do that, 2 times negative 16 is negative 32, g squared, plus 2 times 68, which is 136, and then we still have the g, plus 2 times 2 is 4, okay? So in this case, we had to know how to use the distributive property. We also needed to know, well, function notation, meaning h of g or y, when I guess in this case t is g or x is g, okay? So we plug in g, and then we take it as far as we can. Now in this case, we can't get a number because once again, no like terms, okay? So if we have no like terms, that's as far as we can go with it, okay? We can't add the negative 32 and 136 and the 4, okay? So once again, this has a g squared, this has a g, there's no g, no like terms, okay? So just in summary about the function notation, and this is the last slide of the notes here. Function notation allows us to see the value of the dependent variable for different values of the independent variable. So what I mean by that is if we have f of x is equal to 2x minus 3, that's the same thing as y is equal to 2x minus 3. So we have this equation that's here, okay? Well, function notation now tells us, well, what if x is equal to 1? What's y going to be? Well, that's what we can say when we do f of 1. F of 1 is equal to 2 times 1 minus 3. So this tells us that if we have the x value is 1, what's our y value going to be? Well, it's going to be order of operations. 2 times 1 is 2. 2 minus 3 is negative 1. So what this means is when x is 1, y is negative 1. And that's what it says up here. It means y is negative 1 when x is equal to 1. So we have the ordered pair 1, negative 1. Okay? So whatever's on the inside here, that's the independent variable. Whatever you get out here is the dependent variable, or the value for the dependent variable. So once again, x, y, x, y. Okay? Same thing, if we wanted to know what y was when x is equal to negative 2, well, we plug it into function notation as f of negative 2. Well, do order of operations. 2 times negative 2 is negative 4. Negative 4 minus 3, negative 7. So that means when we have an x value of negative 2, our y value is negative 7. That gives us the point negative 2, negative 7. Okay? So once again, y is equal to negative 7 when x is equal to negative 2. Okay? So we're going to use this function notation. If we know it's a function, we can say, okay, I'm going to plug in this x value. What do I get out for the y value? I'm going to plug in this x value. What am I going to get out for the y value? And since it is a function, if we plug in 1, we should only get one value out. So we should get negative 1. Notice here when we plug it in, we don't get negative 1 and 5 or negative 1 and 23. Okay? Same thing with the -2. When we plug it in, we only get -7. But once again, since it's a function, that means if we plug in -2, we're also not going to get -9 or 23 or 47, okay? Once again, function notation is just a neat way for us to write equations so that we can keep track of our independent variables and our dependent variables, okay? Now, with that being said, that's the end of the notes here. So there will be some practice on this. So if you're understanding, I know this was a giant video, a lot of notes here, okay? But once we get done with some practice and everything, I think everybody will see that this is actually not that hard of a section, okay? Biggest thing is knowing how to do function notation, knowing what it means for something to be a function, okay? And like I said, we'll get plenty of practice with that as we go forward, okay? But other than that, if you do have any questions on anything in the video, anything's not clear to you, please let me know. But other than that, thanks for watching.